This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Legacy materials science focuses on properties that exist only in isolated laboratory conditions. In the field, those metrics are unreliable. When subjected to the friction of real-world use, packaging stress, thermal drift, and mechanical fatigue, the properties of passive substances often evaporate. A material that performs in a vacuum frequently fails once it is integrated into a larger system. Traditional chemistry ignores integration failures. TFR redefines matter as an invariant-bearing phase substrate, valued by its phase logic and deployment role. An invariant is a mission-critical property, like structural integrity, preserved under adversarial transformation. Against heat or force, the substrate keeps its core law stable. This stability enables recursive scaling. The material must function as part of a larger battlefield fabric, a processor backplane, or a sensor array, without its foundational properties collapsing as the system grows in complexity. Matter reaches Realica-grade status once its physical laws are resilient enough to survive deployment. Chemical composition is only relevant if it supports this systemic persistence. TFR's Architectonic Knop sorts matter into strategic nodes by fabric purpose. Class M1 defines structural invariant materials, the load-bearing skeletons. Their primary invariant is geometric continuity under intense mechanical loads. Class M2 covers energetic channel materials, acting as fabric veins, shaping magnetic flux and directing heat. Classes M3 through M5 comprise coherent, topological, and computational matter. These substrates perform logic, protect wave propagation, and embody memory within their state. Beyond physics, the framework emphasizes a classification critical to strategic command, TFR M10, or sovereign provenance materials. M10 materials are defined by strategic control. Entry into this class depends on traceable sourcing, fabrication sovereignty, and a safety-verified lifecycle. Because physical properties are useless without a secure supply chain, M10 binds the substrate to national infrastructure trust. It ensures that the materials at the core of a system are governable and protected from external leverage. Every candidate is also mapped to the deployment horizon axis. A material at F0 is a laboratory singular. It only becomes useful once it reaches F5, infrastructure capable of long-range strategic persistence. The TFR taxonomy is a pre-engineering law. If a material cannot be assigned a fabric role and a viable deployment horizon, it cannot enter the Realica canon. Modern hardware faces a physical bottleneck at the interface between light and silicon. The high-speed transport of optical signals creates friction when forced into rigid electronic logic. Axiom H1 dictates that proximity does not equal integration. Placing optical and electronic components near each other is a structural failure that results in loss-heavy, fragile boundaries. The architectural solution is the Hybrid Optical Electronic Processor Fabric, or HOPF. This system materially co-composes the two domains into a single execution mesh. HOPF enforces a lawful partition. Optics are assigned to high-bandwidth transport and dense interference transforms. Electronics handle decision logic, protocol orchestration, and state retention. This creates a paradox of data persistence. Optical transport is transient and requires constant motion, while memory must be static to hold a state. To solve this, TFR utilizes carrier-to-memory bridge substrates, or CMBS. This is a first-class material layer designed to mediate the boundary between kinetic light and static storage. The CMBS captures transient optical transport and forces it into a persistent memory state. It preserves the structured identity and quantum coherence of the data, even as it transitions from a wave to a block. Capture must be followed by stable retrieval. A bridge that can write data from a carrier that cannot read it back with identical precision is architectonically incomplete. Processing power at this scale requires these identity-preserving bridges. Without them, the speed advantage of optics is lost at the storage interface. Optical and quantum signals are physically vulnerable. Vibrations, manufacturing defects, and thermal gradients instantly degrade standard carrier waves in the field. Topological photonic materials, or TPM, provide the mandatory armor for these channels, shielding them from environmental disorder. In the Realica framework, routing light is not just about guidance. It requires establishing a globally protected law of movement that the signal is forced to follow. By organizing the lattice geometry, the material forces the light into a non-trivial topological state. The signal bypasses extreme disorder and structural defects without scattering or losing amplitude. Local material perfection is fragile. Global topological organization is resilient. The protection is a consequence of the structure's broad geometric class, which ignores microscopic imperfections. This enables the quantum topological fiber carrier network, or QTFC. This infrastructure is designed to host structured light carriers over long distances. Because they ride protected topological routes, these carriers maintain phase coherence and data integrity even when the substrate is subjected to physical trauma. Phase coherence is engineered as a governable material capability that survives deployment, rather than treated as a delicate laboratory effect. Topological armor ensures that mission-critical transport remains unbroken, forcing quantum networks to function despite battlefield damage. TFR employs adversarial checks to determine why legacy advanced materials fail in the field. High performance on a single laboratory metric frequently leads to the novelty trap, where a material lacks a path to integration. Others fail due to interface collapse, shattering under the mechanical stress of real-world packaging. The most difficult failure to address is observer opacity. In quantum systems, attempting to measure a state usually destroys the information it contains. TFR mandates the use of observer interface materials, or OIM, to solve this problem. Axiom 07 states that measurement requires a physical, governable interface. No meaningful data can be extracted without a material layer that mediates the interaction. Observer interface materials act as a non-destructive bridge. They convert embedded physical differences into stable, legible signals, allowing external instruments to read data without disturbing the underlying logic. This enables reproducible calibration. A sensor that destroys its subject or degrades after a single use cannot support a persistent deployment architecture. A substrate is only Realica grade if it provides this legible, non-invasive translation layer between its internal physics and the human or machine observer. The directive of the TFR framework is to move beyond mixing substances. Engineering must focus entirely on fabric law, designing substrates that force physics to behave predictably. Promotion to deployment requires satisfying a mathematical condition. The utility score of a material, measuring its topological structure, robustness, and integration value, must exceed the mission threshold. These microscopic invariants determine the survival of entire processor backplanes. When each node is stable, the entire fabric becomes resilient. These material laws are the foundation for strategic-scale sovereign infrastructure. By engineering the substrate, data transport and processing remain stable across entire national grids. The final strategic imperative is this: by controlling the material substrate, you control the physical laws governing the deployment environment. Advanced materials are the execution layer of sovereign power. The Realica framework is the blueprint for that power's absolute persistence.